The climate hysteria is an example of mass delusion, just as Dick Lindzen says. The climate has always changed and always will, but there's no climate crisis. You don't have to be Sherlock Holmes to figure this out. Dr. Watson is perfectly capable of doing so.
My guest today is Wally Manheimer.
I've had a more than 50-year career at the Naval Research Labs as a scientist in the plasma physics division. I've worked in fusion for about control fusion for about half of my career, and in other various problems in national defense for the other half of my career: radar, microwave tubes, nuclear disturbed atmospheres, things like that. So I have a lot of experience in fusion, both magnetic and inertial fusion. Probably more in inertial fusion than magnetic fusion, because NRL has been active in that until very recently, and I was a participant. More recently, my interest in energy has forced me to look into the climate business. And the reason for that is that my goal as a fusion engineer, the overall goal, was to provide sustainable energy for the 10 billion people who will be occupying this planet in 2050. And of course, I see the climate concern as a gigantic roadblock in this. And especially where, as far as I'm able to read the evidence, the worry about a climate disaster is a false worry. So anyway, I saw the energy part and the climate part is inextricably linked, with, in fact, the energy part being the major part and the climate part being the minor part. And I wrote a book on it called Mass Delusions: How They Harm Sustainable Energy, Climate Policy, Fusion, and Fusion Breathing. The title came from a famous quote by Dick Lindzen, probably the leading expert in geophysical fluid dynamics at this point. And his quote is, "What historians will definitely wonder about in future centuries is how deeply flawed logic, obscured by shrewd and unrelenting propaganda, actually enabled a coalition of powerful special interests to convince nearly everyone in the world that CO2 from human industry was a dangerous, planet-destroying toxin. It will be remembered as the greatest mass delusion in the history of the world, that CO2, the life of plants, was considered for a time to be a deadly poison." And that's a quote I've used many times. I think it's very prophetic. I'm hardly the only one who's written a book on the climate situation. There have been excellent books written by real first-raters such as Steve Koonin, Pat Moore, Michael Schellenberg, Bjorn Lomborg, have all written excellent books on the climate, and I've read every one of them. I'm not so sure. I think I absorbed a lot of them. I'm not so sure I could pass the test on them right now, but they're really all excellent books. And mine has something they don't have. It's mainly concentrates on a particular aspiration I have, which I think is a reasonable aspiration for everyone to have, which is that we need sufficient energy for the entire human family. What we need to get there, how much we have, how much we need, what we have to do to get there, and what's presenting it. So as such, it's one of the few books in the climate energy arena which couples them as a single concept, a single product. And I've published lots of papers in fusion, and those usually I have a pretty easy time to publish, unless I happen to really screw up on one of them, which I've done once or twice, but most of them have been right and have been published pretty easily. The papers I've written on climate, of course, are almost impossible to publish in standard American journals of the quality of, where I published the fusion papers. So I've published them in what you might call minor journals, Canadian, Indian, wherever. But it's one of the few books on fusion breeding. And anyway, when the publishers of this book asked me to put it all together in a single volume, well, as I would say, what does an alcoholic say when you offer him a drink? And that's about how I reacted when they made me this suggestion. So let me go back to some of the other differences besides covering these as a unit. First of all, the book is a lot shorter. It has a lot of color pictures. It's much less scholarly. It's even less politically correct than these other books I mentioned, which are politically correct. And it takes on some sacred cows, which I see as sacred cows anyway, like these prestigious scientific societies, which I think have done tremendous harm. And it's very painful for me to say this. I'm a lifetime fellow of the American Physical Society, and it's the highest honor I was ever able to achieve. I certainly don't have any Nobel Prize to polish up. I'm not a member of any of the national academies. But so I take a lot of pride in being a 50-year member of the American Physical Society, which, like I say, is one of my main scientific achievements, at least as far as societies and societal honors is concerned. And it really sort of pains me to take them on like this and say that they're doing something very wrong and very harmful. It's a society I value, and I think they should do something which not only would benefit the profession by changing their statements and policies, but benefit all of mankind. Don't forget I call them the grand poobahs of, say, these scientific societies. They're not marble statues, which are impervious to criticism. They are fallible humans who I think have made some disastrously wrong decisions. And I'll get to that a little bit later in the talk. My book is also more emphatic. If you look at someone who typically opposes, skeptical about the panic climate, let's say the Wall Street Journal, which I think is sort of trying to operate on both sides of the street now, they'll say, well, it's really wrong to do all this stuff with windmills because, it'll increase the price of electricity by this or that percent. Well, what I don't think they realize, and what I'm convinced of, is that it's much, much worse than that. The transition to windmills has the potential to destroy Western civilization, I think, because we're taking apart our energy system, which works, and which is the basis of our whole economy, our whole military, everything. And I think what we have to remember is that there are powerful, hostile countries out there who are not fooled by the climate mass delusion. There's an old saying that if your enemy is destroying himself, don't get in its way. And the Chinese are taking this one step further. They're getting rich, selling us the rope that we used to hang ourselves. I don't get it. Finally, I certainly didn't write this to enrich myself. If I tried to come up with a hourly salary I got from writing the book, assuming the book really sells a lot, which probably won't, it's probably something like 30 cents an hour. I did it to put into play some serious concepts about both climate and energy, serious concepts which generally get drowned out in a lot of discussions about this. I will say one thing I wanted to do, and it's in the Amazon announcement of the book, is I don't have very many heroes. I probably have a dozen or so. I wrote to like 10 of them and asked them if they could do a editorial review to include in the Amazon ad for the book. And I wasn't optimistic. I felt I'd be very lucky if I got 2 or 3 to agree, and I wasn't even sure of that. But I was really, really flattered that I got 5 of them to agree. And these that 5 agreed, and the 5 or 6 that didn't agree, are all real major leaguers, right at the tippy top of their field. And what I'd like to do is just read very short excerpts from the 5 reviews and who they are. And if you're interested, you can look at the Amazon ad and see the whole review. First is, for readers who want to know about the different options on sustainable nuclear power technology, this is a must. Gus Burkhout from the Netherlands, the head of the Clinton Foundation. This book is fresh air in a world of erroneous views of the world energy system. Doug Lightfoot, maybe you've had him on your show.
I have.
Yeah, he's very much a major leaguer. This is probably one you haven't heard of. They consider our energy level to be something to eliminate it rather than as a goal for all to achieve. The book provides an excellent challenge to this worldview. John Lindell, the head of the successful Livermore experiment on laser fusion, and I was really surprised and extremely flattered that he decided to participate. Those who have not succumbed to the delusions discussed by this book, by Dr. Manheimer, will remain sane if they read the book, and the book will help others recover their senses. William Happer, Princeton, you must have had him on this your show.
Yep.
The book Mass Delusions by Wallace Manheimer is a delightful read, breezily written, irreverent, but always informed. Nat Fish from Princeton, probably their very best of the theoretical plasma physicists at that lab. So I was very happy to get that. Here's the cover of the book. Mass Delusions, How They Harm Sustainable Energy, Climate Policy, Fusion, and Fusion Reading. And look at the book cover. The main image clearly makes the case that if nothing else, these wind turbines destroy the aesthetic, scenic, and tourism value of an area. These windmills they show, I believe, are the four megawatt terminals, which each one is producing 4 megawatts of electricity, assuming the meteorological conditions in wind are just exactly right. These are gigantic. They're about 500 feet high, which is about as high as the Washington Monument. I spent most of my life living in the D.C. area, so I would see that all the time. And that's about how each one, look at how many of them there are. They totally dwarf that tiny little German village below them. However, the harm they do in the scenic values is minor. The book makes the case that these wind turbines, solar panels, backed up by batteries are a disaster scientifically, technically, economically, environmentally, and morally. Unlike what you read in a lot of media, the book shows that they're especially an environmental disaster, as certainly indicated by the cover. Looking at the cover, you can believe that, at least in that respect, they're an environmental disaster. But I said the book is about sustainable energy, how much we have, how much we need, how we can get there, and what's stopping us. So there are 2 other things on the cover. In the upper left, that's the configuration of the successful laser fusion experiment at Livermore Labs. And on the right, that's the schematic of a fusion breeding nuclear reaction. And these both play a major part in the latter sections of the book. So the book's in 5 sections. Section 1 is how much, I think I called it energy from the top down. Section 2 is, I think I called it, the climate always has and always will change, but there is no climate disaster. The 3rd section is some problems with wind and solar. The 4th section is just fusion, and the 5th section is fusion breeding. So let me go through these one by one. And first section, I think, let me show the next slide, and I think we'll just keep the slideshow on here. Here's from the BP, what do they call it? The BP Energy summaries. This was from that 2019 edition. And I think the main thing to look at is the slide on the left. And this shows the amount of energy. The scale somehow is off of here. But basically, these are in terawatts. A terawatt is 1 trillion watts. And it's not something that you familiarly deal with. But if you're in the United States and you have a 100-watt light bulb, you know what that is. If you keep it on for 10 hours, you've used about 1 kilowatt hour, and you've added about a dime to your electric bill. Well, this isn't 100 watts. This is 1 trillion watts. So this is 5 trillion. They're in units of 5 trillion watts. So you can see that in 2020, the whole world uses about 14 trillion watts of every kind of power. And it's your electric lights, your military, your airplanes, your factories, your demolition and construction, everything. And take a look at how unequal that power is. The green below shows that what are called the OECD countries, which are the more developed countries like the United States, Britain, Japan, whatever, which have a population of about 1.2 billion, use about 6 trillion watts. And that's about 5 kilowatts per capita. On the other hand, all the rest of the world, the other 7 or 8 billion people, use 8 terawatts, which means the average person in these other parts of the world are living on something like 1 kilowatt per capita. And that is the problem, as I see it, for the world, not the climate change, but to try to somehow get the world up to a unit of power where it's roughly the same as in the OECD countries. That, to my mind, is the challenge that we're facing. And really, how much longer can the world live with such an inequality in power? I mean, these other countries are not dumb. They're going to do what they need to do to get the power up. And what I set as a goal, and it was totally arbitrary, is let's see if we can get the world up to OECD standards by 2050, mid-century. Well, if you have 10 billion people in the world and they use 5 kilowatts per capita, that means 50 terawatts of power, not 14. And realistically, you don't need that much. You probably need 35 or 40 because the efficiency of power gradually increases as you proceed. We're using power a lot more efficiently than they did 50 years ago. And 50 years from now, we'll probably be using power more efficiently than we are now. So figure something like 35 or 40 terawatts you need by 2050. So basically, you want to add something like 20 or 25 terawatts to what we're producing now. And we want to do it by 2050, which may or may not be possible. Maybe you have to do it by 2070, but let's just keep 2050 as a guide point. So you have to add something like 7 terawatts per decade. And as you can show, BP is predicting that we're only adding something like 2 terawatts per decade. So we have to add power about 3 times as fast as BP projects that we're doing it. And this is what I see as the problem. And if all of this is done, if this whole 40 terawatts is done by fossil fuel, I guess my feeling is we'll be putting a lot of strain on our fossil fuel industry. And yeah, I don't know how much fossil fuel there is, or when we'll run out of it, but we'll run out of it in 1/4 of the time if we run it at 40 kilowatts than if we run it at 10. You can see that the fossil fuel over here is producing about 12 terawatts. So if it's producing 35 terawatts, we're going to run out of fossil fuel in 1/3 the time as if we keep using it at this rate. So I see us using it at this rate. It's also not putting dangerous amounts of carbon dioxide in the atmosphere at this rate. And I think the only way to make up for it is with nuclear power. So BP doesn't see renewables playing that much of a role, at least up to 2040. And they still say that we're going to be relying on fossil fuel, which are these bottom 3. It also doesn't see us doing much with nuclear. And that's where I tend to sort of disagree with him. I think the hope of getting the world to full power for every citizen of the world is through nuclear power. So what I'd like to do is talk a little bit about the sort of nuclear reactors that we have. Whoops, wait a minute. Oh, here we are. Okay, probably have heard of uranium-235 and uranium-238. And for these very high atomic number atoms, which are called actinides, the ones with odd atomic weights in the presence of neutrons behave very, very differently from the ones with even atomic weights. What I'm showing here is the fission cross-section. And if you don't know what a cross-section is, it's basically how likely is it to produce this sort of reaction. And the energy of the neutrons in electron volts. And again, don't worry if you don't know what an electron volt is. There's here like a 6 or 7 order of magnitude variation in the energy of a neutron. And it's something like 1/10 of a neutron volt. That's something like an oven temperature, maybe 1,000 degrees. And it's something like 1,000,000. The energy would be really something like if it was the temperature of maybe 10 billion degrees. So don't worry so much about what these are if you're not familiar with the units. But you can see that in odd atomic weight nuclei, as you lower the energy of the neutron, which is bombarding the atom, the fission cross-section, the rate to which it produces nuclear fission, goes up enormously by maybe 4 orders of magnitude as you get from the billion temperature to the thermal oven temperature. The rate of fission just goes up enormously. So this is why they always wanted to do odd atomic number atoms, and this is what they do. And these neutrons are generally produced at an energy of about 2 megavolts. So at the energy at which these neutrons are produced, it's very difficult to get them to react and to do fusion. And that's why a big effort is to slow these neutrons down. And that's something the nuclear industry knows how to do and does pretty routinely. But you can also look at U-238. And again, these neutrons are produced at the megavolt level, which is over on the right-hand side. And it's possible to get a reaction to go with those neutrons too, but it's much more difficult. But it's been done. And an advantage of that, not only is that it can breed more fuel from the uranium that's in here, but any of these actinides, it burns at about the same rate. After a look at the fission rate of U-235, it's around 1 at this highest energy. And of U-238, it's the same, but then it drops. So there's a certain advantage to building a reactor which can go at these higher energies, and they're called fast neutron reactors. And they've been built, but they've been very difficult. The Russians actually have 2 of them and hooked up to their grid. The one they call BN-600 and BN-800. And by the way, the Russian word for fast is bistro, so you can see how they got the name. And the French for a while had Phoenix 2 hooked up. Phoenix 2 they had terrible time with. They finally got it to work. A thermal nuclear reaction, the standard kind, for your coolant, you can use almost anything, water, air, graphite, whatever. For a fast neutron reactant, you're much more restricted. The main one is liquid sodium is the only coolant that you can use. So you can imagine how much more difficult that is. But let me just talk a little about the light water reactor here and what a typical light water reactor is. And a typical light water reactor has my guy mowing my lawn. The typical light water reactor typically takes in about 25 tons of fuel each year. About 24 tons is U-238, and about 1 ton is U-235, which is really the fuel. And each year it spits out a waste product. And this waste product is typically almost all U-238, which went along for the ride, but is there for other important reasons. You get about 200 kilograms of plutonium and about 800 kilograms of what are called fission fragments, highly radioactive intermediate atomic number atoms like, maybe krypton, barium-137, strontium-90, cobalt-60, whatever. You get this big stew of radioactive elements. But I think the thing to remember is that you're putting in 1 ton of fuel, U-235, and when you take out and refuel it, you're taking out a fifth of that, 200 kilograms of plutonium-239, which is also a potential fuel. Now, the intermediate atoms have a half-life of about 30 years typically. So these you can actually store for a period of something like a few hundred years, and they'll be inert, or at least not so much greater than the background. The real problem is plutonium. That has a half-life of 24,000 years. And not only that, it's not only a fuel, it's enormous proliferation risk. So this is one of the real problems of nuclear power, is what do you do if the plutonium waste comes out? And we'll talk about that in some more detail later. But another long-term problem with nuclear reactions is that there's very little fuel. I mean, the amount of U-235 is tiny compared to the amount of, say, oil, coal, or gas when you measure it in energy. So the U-235 is something you can see running out of if the world turns to nuclear at a fast rate, and if 10 billion people are using it. So the only hope really for the long term, for the sustainable, is you've got to breed fuel from these elements like U-238, which are called fertile elements. And you can breed either with fission reactors, like what we've talking about, or with fusion reactors. And one of the main points I've made over the years is my scientific career is that we can breed with fusion. So that's probably about what I want to say about the nuclear. And like I say, I see the hope for the mankind to get all of this by 2050, or pick whatever date you want, is you want something like 30, 35, 40 terawatts of power, which most of us should be supplied by nuclear, and maybe less by fossil fuel, and less still by windmills and hydro and all that. Let me talk a little about the second part of the book. Then the climate always has and always will change, but there's no climate crisis. And I think there's a term which someone introduced. Bjorn Lomborg was one of the authors of the book, and he introduced a term which I've certainly started to use, and he's used a lot, which is the climate industrial complex. I'm old enough to remember when President Eisenhower in his farewell speech talked about a military-industrial complex. And Lomborg takes that. Let me use the quote from Lomborg, and I'll read it. President Dwight Eisenhower famously warned about the might of the military-industrial complex, cautioning that the potential for the disastrous rise of misplaced power exists and will persist. He worried there's a recurring temptation to feel some spectacular and costly action could become the miraculous solution to all the current difficulties. This is certainly true of climate change. This is Lomborg talking. This is certainly true of climate change. We are told that very expensive carbon regulations are the only way to respond to global warming, despite ample evidence that this approach does not pass a basic cost-benefit test. We must ask whether a climate-industrial complex is emerging, pressing taxpayers to forego over money who stand to please those who stand to gain. Lomborg, by the way, is one of the individuals that Time magazine called one of the 100 most important thinkers of the world today. So this guy is a real major leaguer. And there are, I've characterized two types of people on the climate problem, which I've called the Chicken Littles and the naked emperors. And if you remember your children's books pretty well, I think you know what I mean by each of those. And I'll give three examples of this trick. And these are both sort of the Chicken Littles and the Naked Emperors. The first is James Hansen, who in 1988 sort of started the concern over global warming from carbon dioxide. And he did some numerical calculations from what were the best scientific results at that time of how much the world would gain in temperature, how much the world temperature would increase by 2011, with various assumptions for how much carbon we were putting into the atmosphere. And he had three. A, we're putting in increasing the carbon by 1.5% each year. B, we're just putting carbon into the atmosphere at the fixed rate. And C, we stop putting carbon into the atmosphere. And here are his three calculations. The blue is for the most carbon we're putting in. The B is just for if we had, it just as if we fixed the carbon dioxide at the level we were putting it in 1988. And C is if we stopped putting it in altogether. And these are his calculations, the blue, the red. The black is actually the observed temperature. Now, how much carbon dioxide did we actually put into the atmosphere? We actually put in a whole lot more than his curve A. We put in a lot more than a gain of 1.5% per year. So he is just way off by orders of magnitude. And he's not the only one who missed it. There were many simulations of what the temperature would do with various carbon inputs. And John Christie presented to Congress. He's one of the guys who really follows this stuff very carefully. He presented to Congress all of these models, and you can see all of his models up here, and the actual temperatures are in the blue circles and the green squares, and these were the actual measurements, and you can see that the predictions are way off. They're predicting much more of a heating than you would think there would be from the carbon dioxide in the atmosphere. And these codes clearly are not making random errors, because if they were making random errors, there'd be just as many predicting too little heating as too much. So you've got to believe that in these simulations, there's a strong bias for heating, which is built into the codes, and it shows that. Now, I haven't followed the simulations very much after that, and what I would guess is that if you look at the simulations done now, you would see something that exactly matches what we have now, but then shows that in 20 or 30 years, we're going to be courting catastrophe. Well, I say, how many bites from the apple do these guys get before you stop believing them? There's a famous quote by John von Neumann that says, "Give me 4 parameters and I can simulate an elephant. Give me 5 and I can get him to wiggle his trunk." And these codes have many more than 4 and 5 parameters that these people are putting in. In here, John Christie actually has citations of the actual people that did these simulations. So anyway, regarding simulating an elephant with 4 or 5 parameters, a couple of guys tried to do that, and guess what? They succeeded. Here are their simulations of the elephant with 4 parameters. It's just one of these, but by varying a 5th parameter, get the elephant to wiggle its trunk. So this shows what you can do with simulations if you want to get one result. And I just got a kick out of this. Well, I think the main Chicken Littles and Naked Emperors are the ones that I mentioned at the outset, the American Physical Society. And as much as it pains me to go through some of what they've done, here it is. Let me move this. Here's their statement on the global warming. It's a much longer statement than this, but this is what I think is the most important part. multiple lines of evidence strongly support the finding that anthropogenic greenhouse gases have become the dominant driver of global warming, a dominant driver of climate warming since the mid-20th century. Notice I say the dominant driver of climate warming. So that means you would expect, I think it means you would expect to see that since a lot of carbon dioxide has been put in the atmosphere, the temperature has been warming faster than when you aren't putting carbon dioxide in the atmosphere. That would seem to be an elementary conclusion from what they say. But this statement is absolutely wrong. All you have to do is look at a NOAA plot of the world temperature, and they're all over the place. Here they are. Take a look at the temperature rise from 1910. Take a look at the temperature rise from 1910 to 1940. It increased by about 0.6 degrees centigrade, and it's about 0.2 degrees centigrade per decade. Well, then keeps jumping. Well, then from 1940 to about 1980, it bounced around sort of constant. And then from 1980, which is when carbon dioxide went into the atmosphere, was really going seriously into the atmosphere, it increased from about 0.2 to about 0.8. And actually, recently, it has been actually falling a little bit in the more recent years. So it's a slower rate of increase than there was from 1910 to 1940. So what the APS says just couldn't be right. And it, like I said, it's painful for me to say this, but how can they make a statement like this, which is just obviously wrong? You don't have to be Albert Einstein to see that it's wrong. I mean, all you got to do is get a NOAA graph. I mean, you can look on the upper left of the graph. There's a NOAA icon on it. This is, about as authoritative as you can get. Well, they might say, okay, well, maybe it's increasing just as fast. But look, it's higher than it's ever been now. So we're at a record high temperature. Well, that's wrong again. This is not a record high temperature. You can look at and I do it in the book, you can look at the temperature in the period of human civilization by a number of signs. And some of the best of these signs were done by physicists. The APS is ignoring the tremendous calculations of its own members but just I don't know why they do it. Just to grovel to the climate industrial complex. I'll talk about that more in a minute or two. But there are ways you can get very good ideas of what the temperature is in the whole period of human civilization, and I'll show you that in a sec. But basically, one of the main things is that oxygen occurs in two isotopes. The main isotope, which is 99.9% of the oxygen, is oxygen-16, where the nucleus has 16 protons and 16 neutrons. But about 0.1%, or 1 in 1,000 oxygen atoms, is oxygen-18, where the nucleus has, where the nucleus has 10 neutrons rather than 8, and it's a little heavier. And the ice caps on Greenland are formed by water which evaporated from the oceans in large parts of the world, which are south and west of Greenland. And the wind carries the moisture up there. It turns into snow, and it's from the prevailing westerly winds and from the general circulation. So the snow that falls on Greenland comes from a large part of the oceans in the world. It's not local to Greenland by any means. And water evaporates. Water with oxygen-18 evaporates slightly slower than water with oxygen-16. And not only that, the differences in these rates are dependent on temperatures. So looking at the isotope ratios in various levels in the Greenland ice cores, you can get a pretty good idea of the temperature going back 10,000 years. And it shows periods of oscillations between cold and warm spells. And let me put the graph on. And the thing about this that gets me is this. Here's the graph. This was done by physicists. I mean, they're the ones that understand the isotopes. They're the ones that understand the difference in rates of evaporation. And the differences between the two isotopes are, of course, tiny. There's just a tiny amount of oxygen 18, and the differences in evaporation rates are tiny. So it's the physicists that not only pointed this out, but they're the ones that figured out how to get this very noisy data, which they see, and actually treat it as best they can to get an idea of what happens at various times. And here's the graph they came up with. And this is with a lot of averaging. A graph of the actual data looks something like this, but it's much choppier. This is averaged over it. And about 7,000 years ago and about 4,000 years ago, there's a warm period called the Holocene optimum. About 2,000 years ago, there was a warm period. About 2,000 years ago, there was a warm period called the Roman climate optimum. About 1,000 years ago, there was the medieval climate optimum. Between them and now, there was a little ice age. And the isotope ratios are hardly the only ways you have of confirming this. One of the main textbooks in climate science, this is called The Climate History of the Modern World by H.H. Lamb. And he goes through many other signs, and they basically confirm this. And let's take a look at one of Lamb's graphs. What he does is he takes a look at where the northern forests end. And the red curves here are the northern limits of where the northern forest ends. Whoops. The blue curves over here are where they ended 4,000 years ago in the Holocene optimum, about the time of the biblical Exodus. And you can see that 4,000 years ago, the forests extended about 200 miles closer to the pole, just like you might expect from seeing the Holocene optimum. Same thing in the North American continent. And these are worldwide measurements. I mean, they're in Siberia, they're in Norway, they're in Canada, they're in Alaska, they're everywhere. And Lamb had other examples of this sort of thing too. The timberline in various mountains in Scotland 4,000 years ago was much higher than it is today. And like I say, the remnants of what happened 4,000 years ago are still there. And this is elementary. This is the elementary textbook of climate. And the American Physical Society ignores it. Well, let's look at some other signs. In the Roman climate optimum, they grew wine all over England. And after the Roman climate optimum, no one grew wine there anymore because England was too cold. Nowadays, about 150 years ago, cold weather grapes were developed, and there are fine vineyards now in Minnesota and Quebec. But that isn't true in the Roman times. They didn't have those grapes. So, they grew wine all over England. You can see them right up to Hadrian's Wall. They grew grapes. They had vineyards, and there are archaeological finds of these vineyards, and they're still there, and you can dig and find them. And so, certainly in the Roman climate optimum, the weather was warmer than it was after that. I mean, I'm sure they grow fine vineyards in England now, but this was as the variations of grapes became more consistent with the English climate. But for 2,000 years, they couldn't grow decent wine there. Another one is in the medieval climate optimum. The Vikings grew barley in England, and modern explorers in 2012 found some of this barley grain. They carbon dated it and found out that sure enough, it was from 1,000 years ago. And you can't do that now. So in the medieval optimum, it was warmer than it is now. So all of this data, the American Physical Society just ignores. And it's irresponsible, I think. I'll go through one more. Okay. Yeah. Okay. Let's take a little look at the physics of radiation in the atmosphere. And the interesting thing is both the IPCC, which are the guys who are promoting the climate disaster coming, and the skeptics, mostly I'm thinking of Weingarten and Hopper, calculate the excess average solar radiation coming from carbon dioxide. And both of them get about the same results, something like 0.5% to 1% of the solar radiation coming, the average solar radiation coming to the Earth is modified by carbon dioxide. Well, what is the law of regulating the temperature and radiation? Well, it's the Stefan-Boltzmann law. And this is something physics majors learned in the sophomore and junior year. I think in my education, I learned it in the junior year, that if you have a black body with whose temperature is T, the absolute temperature is T, the amount of radiation goes as T to the temperature of the fourth. And this is just the standard law for black body radiation, or the relation relating radiation to temperature. Well, look at it in reverse. If you know what the radiation is, the temperature goes with the radiation to the 1/4 power. So if you're increasing the radiation by 1%, and if it obeys the Stefan-Boltzmann law, which is the fundamental law, I mean, if it doesn't obey that, you got to have some sort of explanation to why not. If it doesn't obey that, you're talking about 1/2 or 1% more radiation means 1/8 or 1/4% more change in temperature on the absolute scale, or less than 1 degree centigrade. In short, much less than many other things. And it's more complicated than that. Weingarten and Hopper, for various assumptions of how the atmosphere and the various greenhouse molecules react to this change in radiation, they come up with a little more than that. But they come up with something like maybe 1% change in solar radiation gives you something like 0.5% degree instead of 0.25%. And so you'd see maybe a little more than 1 degree change. But the APS just ignores the most standard law, which every high school graduate, every college physics major knows. So why does the APS go along with such obviously false statements? I can't read their minds, but it's hard to dismiss two possibilities. One is that they didn't even do minimum due diligence. They didn't look at the work of their own members finding the fact that the temperature is oscillated between warm and cold periods. Or also, worse, they realized that dollars are available only for supporting the false temperature crisis. So as Alexander Pushkin said, which I heard in English from Will Happer, put out a trough and the pigs will come. And Happer showed this slide of a trough put out with the pigs coming. I'll just go through one more Chicken Little and Naked Emperor. And this isn't the American Physical Society. This is Marcia McNutt. I think in the mid-teens, around 2012, I forget exactly when. She was the president of the National Academy of Sciences. Someone who's obviously very, very bright. And she'd put out an editorial in Science magazine for which she was the editor. And she says, but now with climate change, we face a slowly escalating but long-enduring global threat to food supplies. to support a population of more than 7,000 people. And here's what really gets me. The time for debate has ended. We can't talk about it anymore. Action is urgently needed to reduce the per capita fuel emissions even further. Well, she says that it's a threat to food supply. It's not hard to find out what the food supply has been doing. All you got to do is type into Google Images or Bing, give me a graph of the increase in food supply over the years. And here it is. Oh, she also does one other thing in the article. She actually puts in this. This is a picture of one of the circles of hell from Dante's Inferno. And she says that people who deny the presence of a climate crisis, you have to be put in one of these circles of hell. And she actually has the picture of it in her Science magazine article, which I have to say is unique for Science magazine. I've never seen anything quite like that. But anyway, you look at what the food supply is doing. And this isn't the food supply. This is the per capita food supply in calories per person. And it's increasing everywhere in the world. My God, recently it's even increasing in Ethiopia, so if there's any long-lasting threat to the world food supply, there's certainly no indication of it now. And why didn't Marcia McNutt go to Google Images to take a look and see whether what she said made any sense or not? I mean, it makes no sense. And yet there it is, right in the chief editorial of Science magazine, one of the main, most prestigious science magazines we've got. So anyway, that's sort of my examples of the Chicken Littles and the Naked Emperors. What I'll talk about now for a bit is some of the problems with windmills and solar panels. Well, for one thing, you've got to realize when you do with solar panels and windmills is that when you look at the published power, what's usually published is the nameplate power. This is the power that the device, the windmill or the solar panel, gives to electricity when the conditions are exactly right. And of course, conditions are rarely exactly right. Typically, the average power, which is certainly the more reasonable number, is averaged over all conditions. And that is typically about 1/3 to 1/5 of what the nameplate power is. And you don't read that when they talk about the power. They talk about only the power. And an interesting example to it is the Topaz Solar Facility in California, which at one time was the largest solar facility in the world. And I think what you've got to do, how much these are restricted by, is what is the power, if you want to do solar power, whether it's wind or solar, it's restricted by how much solar power is coming to the Earth. And at high noon on a summer day in mid-latitudes, with a cloudless sky, the solar panel coming to the Earth is about 1 gigawatt, which is about 1 billion watts per square kilometer. Well, you average over day and night. Let's do it for solar power. You average over day and night, and that brings it down to half. You average over solar angle, over sun and snow and cloud and wind, and you get its averaged over all conditions is something like 200 megawatts per square kilometer. The typical solar panel have efficiencies of something like 10 to 20%. And I think 20% may be more what is available now, or I use more now. It certainly used to be around 10%. So 200 kilowatts per square kilometer is coming down from the Earth on the average. The solar power converts 20% of that to electricity. So that's 40 kilowatts per square kilometer. So to get a 1 gigawatt power plant, you need 25 square kilometers. If it's a 10% efficient solar panel, you need 50 square kilometers. I mean, that's a lot of land for one power station, which if it were gas powered, it might take a couple of acres. And here's a picture of the Topaz solar farm in California. And as I said, at one time it was the largest in the world. It's not anymore. But anyway,
I'm sorry, Wally. Let me ask you. What is the size of it online? I think it says it's 25 square kilometers. The Topaz.
25 square kilometers for a 20% efficient. 20% efficient. That is, yeah, it's 40 kilometers. If it's a 20% efficient solar panel, and it's 200 megawatts per square kilometer, that's 40 kilowatts. That 40 megawatts that you could get per each square kilometer. So to get a gigawatt, you need 25 square kilometers. So that's a lot of land, especially in a place like the crowded, cold and snowy Midwest or Northeast. And here is the solar. And here's an example of it. This is in very sunny California, and it's 13 square kilometers. And they build it as something that gives 580 megawatts. And the cost of it was $2.5 billion. But then read the fine print of it. It gives you the total power in megawatt hours or whatever. And you see that when you divide that by the number of seconds in a year, the average power is only 130 megawatts, not much more than 1/5 of the power they advertise it as. And that's one of the things about both solar and wind. You very rarely read average power unless you go into the fine print. And even now, this facility is running into trouble. At least a year or so ago, when I looked at it for the book, it was toying with the idea of bankruptcy. Well, wind, of course, is even worse. Only 1 or 2% of the solar power on Earth is turned into wind, but a windmill is actually possibly a little more efficient. That's what's called the Betz limit, and that might be 60% efficient when everything is happening just exactly right. So a 1 gigawatt wind power farm is 500 square kilometers. And that is really a lot of land. And there's not a whole lot else you can do with the land. I mean, you saw the cover of the book. There's not much you can do with that except grow plants, maybe graze animals. It's just not fit for people with the noise and the vibrations. And especially in the cold regions of the country or in Germany, when it throws down chunks of ice that are, a couple of 100 kilograms, and you wouldn't want to be hit by one of them as it fell from 500 feet. I guess if it hits a cow or a pig, it doesn't mean any difference, but it's certainly not a place that humans can go safely. And it's unreliable. In hot days and snowy evenings, there hasn't been very much. It's failed many times. In the summer of here it was for the winter of 2021 in Germany. The solar panels became covered with snow. The wind turbines basically became frozen, and they were without power for many weeks in the winter of 2021, January and February. And here on the left is how the German school kids did their homework. And that following summer, California experienced something simple with the solar and wind conking out just when they needed the most power for air conditioning. And it's just unreliable. You need some sort of a backup. And people are talking about battery backups, and it makes no sense. If you look at the Tesla battery, which is probably about the best and most reasonable battery now, a Tesla battery costs about $10,000 or $15,000, and it stores about 100 kilowatt hours. If you could reduce the price from $10,000 to $1,000, and you figure out how many, that you need maybe 5 or 6 battery banks in the various spots of the country to produce power for maybe a week or 5 days or something, you add up the cost of it, it comes out to something like $600 trillion. I mean, it makes no sense just for the backup of it. Another aspect of solar and wind is that it just takes a tremendous amount of material. And this is something that Mark Mills of the Manhattan Institute has studied very carefully. Whoops. Oh, here it is. Somehow Oh, okay. Here is the energy according to one of Mark Mills. The references are all in the book. For solar PV, you need, my God, it's at least 10 times more material, probably more than that, than you do for like a natural gas plant. Same thing for wind. It's, the fuel is free, but the capital cost of putting these things up, and in the case of wind, these are, for every megawatt of power, you're putting up something the size of the Washington Monument. I mean, these are big, and they take up a lot of room. And this is the material, and nobody's talking about where you mine the material. And not only that, we typically try to get these materials from like China or from Africa. The mining regulations in this country, which are environmentally done, almost forbid it. That have to all be rewritten. So we go to Africa. We don't mind trashing their environment, so we can have this presumable green energy source. But you're trashing somebody else's environment, and not only that, a lot of the materials that go into solar panels and wind are rare materials like rare earths. They use a lot of cobalt, a lot of nickel. These materials are not safe to put in landfills, and they'll leach into the water supplies and things like that. So you can't really put them in landfills. And the solar panels, well, first let me talk about solar panels. Now we have about 250,000 tons of worn out solar panels, which we've got to put somewhere. And even environmentally conscious California is cheating a little and putting a lot of them in landfills. But the thing that really gets me is once they're worn out, we want to ship them back to Africa. I mean, it's not enough to trash the African environment due to their loose mining regulations. We want to do it further by sending them the garbage that we can't dispose of safely in our own country. And we call it a moral issue to do this. Well, how moral is it from the Africans' point of view? Not very. So doing that, I see these as an environmental disaster. The 250,000 tons which we disposed of last year of solar panels, now that they're much more common, we're going to have to dispose of well over 2 million tons per year in the future. And where do you put it? How do you do it without trashing your environment? And they say, okay, and this is one thing that, one of the very few arguments I have with Steve Koonin is he admits that when things are working exactly right, solar and wind are the cheapest power supply. And I tend to dispute him on that. I said, well, what if they are? Even if they are, which I doubt, there's one thing that really can tell you. I mean, you can read all sorts of articles about how cheap they are and why aren't we using them now? Well, there's what I call a vast laboratory in Europe, and it's Germany and France. France has, for decades, a nuclear infrastructure for their electricity. And they've done this without impoverishing themselves, without trashing their environment, and without creating any proliferation risk to speak of, and without strangling in bureaucracy every time they want to put up a nuclear power plant, and without having to fight 10 years or 20 years worth of lawsuits before they put up the power plant. They've just done it, and it produces their electricity. And the Germans, though, in about 2000, have taken a different approach. They've done what they call the Energiewende, which means the energy transition, and they're going to transform their energy supply from solar and wind to the extent possible. And look at the cost of a kilowatt of electricity in the two places. In France, it's blue, so it's this blue line starting at 10, decaying that. These are in euro cents per kilowatt hour. In France, it started at 10 cents, decreased to about 7. Now, recently, it's increased to about 10 again. But look at Germany. For a long time, they were cheaper than France. And then when they did their energy Wende, and their power is very much subsidized by the government, it's like 4 times what the French pay, 4 times what the Americans pay. And there's no disputing this. This is what people are actually paying. And what's really scary is I forget the number, maybe in the low millions or high hundreds of thousands of Germans who were cut off from the grid because they couldn't pay their electric bills. And they must be really angry. And if there's one thing history teaches us, I guess, is you really don't want to get the Germans very angry. And you can see what's happening, and the growth hasn't stopped. So it's not cheap. It's the most expensive, and it's also the most dirty. Let me talk a little about here. Let's say you have a perfect way of disposing of the solar panels. They're still exposed to the weather. And here's a picture of solar panels in the Virgin Islands after Hurricane Maria came. I mean, it just trashed the whole thing. It must have done tremendous damage to their environment there. Who knows what it's doing to their water supply? Let me go into windmills a little bit. Windmills, when they're worn out, what do you do with them? Well, it sort of reminds me of the Tom Lehrer song of Werner von Braun. Once rockets go up, who cares where they come down? That's not my department, says Werner von Braun. And I should have sung it maybe. And here are some worn out windmills. Here's near Harlingen, Texas in 2017. Here's on the North Shore of Hawaii in 2018. They just left them there for some period of time. I guess they might have taken them down. But you have to take down, and these are the smaller windmills. You've got to take down windmills that are each one the size of the Washington Monument. And that's got to be very expensive. And the temptation for the wind power company, of course, is just to disappear and leave them there and let somebody else worry about it. As Tom Lehrer said, it's not their department. They're too busy saving the world. They can't worry about such trivia. Here's the Oklahoma Panhandle. And these look like the larger 4 megawatt, 500 foot panels, although it's hard to say because there's nothing to compare them against. But just from the looks of them, I would say these are the more modern ones. And okay, maybe there's some salvage value for these, but there's but it's certainly not. It certainly must be very expensive to take these down, even if you cover some of the salvage value. I mean, probably the stalk is metal, and you can get some money from that, from scrap metal. But one thing you can't recycle or salvage is the base. Here's a picture of a base of one of these 500 megawatt, 4 megawatt, 500 foot windmills, which has been taken down. There's 500 tons of steel and concrete, and it's not going anywhere. And I can just see 500 years from now, our descendants will wander around a place like this. And as I said, they'll look and say, my God, what are these things that their primitive ancestors built? And why the heck are there so many of them? And like I say, these aren't going anywhere. They're just going to scar the landscape for probably thousands of years. So in summary for these wind and solar panels, people have estimated the cost for the transition. And even in IEEE, which is a very respectable magazine, they think the cost of the transition over the next few decades is $275 trillion, for which we're not spending nearly enough now. And these enormous figures seem to be simply accepted by the public, and it seems to me to be a proof of mass delusion. And I'll just read the last paragraph in this part of the book. After all, this is our money, and it's a tremendous amount of it. Why is nobody asking questions like, do we really need this? How much will I have to pay? Just exactly what do we get for it? Does it really save the planet? What do the opponents of it say? What do thousands of scientists who oppose it say? Why are they being canceled all over social media? If a temperature rise of a degree and a half centigrade from the pre-industrial value will produce catastrophe, how come the temperature we've already experienced of about 1.1 degree has produced only benefit? Are there better things that we can spend 275 trillion on? Are we being like sheep marching calmly to the slaughter, lemmings rushing to the cliff? And a little summary I have to plagiarize from Lindzen. What historians will definitely wonder about in a few centuries is how flawed logic, obscured by shrewd and unrelenting propaganda, those who want to profit, actually enabled a powerful coalition of powerful special interests to convince nearly everyone that the world's power structure, which basically works, must be replaced with another one which will fail, and along the way destroy modern civilization. It'll be remembered not only as the greatest mass delusion, but also as the greatest con in the history of the world. That snake oil salesman at one time convinced the world to spend $275 trillion to throw out its working power system and replace it with a harebrained Rube Goldberg gadget. So that's sort of my conclusion on some of this. But let me talk a little about fusion, and I'll try to be quick since this has taken a little more time. The basic fusion reaction is you take a deuterium and a tritium atom, and they join together to form, I'd call it a heavy helium atom, a helium atom with a helium nucleus with 2 protons and 3 electrons, which is unstable. So it spits out the remaining helium atom, which is at about 3 megavolts, and a neutron at about 15 megavolts of energy. So the energy multiplication is about 400 to 1, 450 to 1 from the atoms going in to the atoms coming out. And there are 2 ways of trying to pull this off, because the atoms coming in happen to be very hot themselves, not as hot as what comes out, but very hot that no material construction can hold it. So you have to do it in one of 2 ways, which we've thought of so far. One is hold it in a strong magnetic field, which is which holds it together for a little while, but not very long. And you pump in the helium and the deuterium atoms. You just sort of feed them in, and also you feed in something which heats them to the point where they can form this reaction. And I would compare that to like burning wet wood with a blowtorch. The wet wood is the helium and tritium, but but it can't burn because it's wet. So you have a blowtorch blowing on it, and that dries it so that it can burn. And of course, you will expect to get a lot more energy out of the fire of the wet wood than you're putting into the blowtorch, which dries it. But that's sort of a very simple analogy for magnetic fusion. There's inertial fusion, which compresses, this is sort of a tiny hydrogen bomb. It compresses a tiny little element of fuel until it reaches these fusion temperatures, and then it burns. And the analogy for that is a spark plug. You fill up the chamber with the right air and fuel mixture, and you send a spark through it, which ignites the whole mixture. So it first ignites it around the spark, and as it heats up, it heats the whole fuel mixture, and then the whole thing finally burns. So if you can pull that off, the energy ratio almost becomes irrelevant as long as you can get Like in a spark plug, the energy of the spark is a whole lot less than the energy you get from burning the fuel. So those are the two analogies. And fusion has been around for about 60 years, and it's made a lot of progress, but it's also been confronted with long delays and big cost overruns. Magnetic fusion, I'll just put the magnetic fusion configurations. The world's countries are now combining to build something called ITER, which is a device called a tokamak, which here is on the left-hand side is a schematic of the tokamak. And it's basically a big vacuum chamber surrounded by a toroidal magnetic field. And on the right-hand side is the construction that's happened so far in ITER. And what ITER hopes to achieve is that by putting in 50 megawatts of beam and microwave power, they can get about 500 megawatts of fusion power out of it. So 10 times more than what they put in. And it's an enormous facility. It was originally supposed to be $5 million and turn on into $5 billion and turn on in 2016. Now it's at least $25 billion. And if the optimistic proposals they have now are really correct, it'll turn on in 2025 and perhaps get this 10-time improvement in energy by maybe 2040. But even this is nowhere near what you need for fusion, because a factor of 10 doesn't account for the inefficiencies of converting fusion power to electricity. And it doesn't account for the fact that these beams and microwaves that you put in are also quite inefficient. So if they get ITER to work, then the next step is an even bigger project called the demo. And what this has to do is it has to be smaller and cheaper than ITER, obviously. And it has to be more powerful and have a higher Q, a higher efficiency, a higher ratio of power to input power. Realistically, nobody has a clue how they're going to do the demo. So this is this is after 60 years, and you're talking at least another 60 years before it gets on. And people have argued that they can do it in 10 because it's in the private sector and private financing. The book argues against that and says it's very unlikely that this is going to work. Let me turn to laser fusion. Okay. Yeah. Laser fusion, again, there's been a lot of smaller lasers building up to a large laser in Livermore Laboratory in California. And in a way, the story is not so different. It was approved in 1995 for $1.1 billion. It was finally finished in 2009 for $3.5 billion. And so it's sort of like ITER, but on a much smaller scale. And they were supposed to have ignition. That is, they were supposed to have a gain of 10, produce 10 times more fusion energy than the laser energy in 2012. Well, they did get the thing working. The laser now works very well, and they get multi-megajoule pulses, and they're about 10 nanoseconds long and 10 billionths of a second long. And here, before they got anything, here are some of their images of how they expect to go. Here's the building that it's in. So it's about half a kilometer this way, maybe a quarter or a third of a kilometer this way. It's a gigantic building. And in it, it's all filled with laser bays, which are here in the lower left. And the laser light comes into a big steel ball, and it's focused on a target, which is in the middle. And the target's about 1 millimeter in size. And what they want to do is hit the wall. The target is in a configuration called a hull room, which is some high Z material like tungsten or uranium or gold. They focus the laser on the wall of the material, and it produces a very intense X-rays. And then these X-rays actually implode the target and get it diffused, they hope. It was supposed to fuse in 2012, and in 2011 there was a laser fusion meeting in California near Livermore, sponsored by Livermore, and the title of their meeting is "Laser Fusion on the Eve of Ignition." Well, it was a pretty long eve. What they hoped to get was a gain of 10, and get it in 2012, and unfortunately, nature didn't cooperate. The first gain missed by about 3 orders of magnitude. It was about 1% instead of 10. And they worked and worked for 10 years. It was finally in 2021 that they really got something that was good. And despite my denigrating them by what I just said, it's just an amazing experiment. Here is their target. It's DT, deuterium and tritium, and it's held together by DT ice and another outer shell, which holds it all together. They have a 10 nanosecond, about a 10 nanosecond laser pulse initiating it. And here's their schematic of the laser hitting the sidewalls of the hull room and producing the X-rays, which let them implode the target. And here's their vision of imploding the target. And in 2021, they actually produced something which I think is really rather amazing. And in fact, I think that 100 years from now, this experiment is going to be regarded as one of the key experiments of the 21st century. And when you produce this hotspot in the middle, which fuses, you produce both alpha particles, which are very energetic, but they just deposit their energy locally. And you also produce neutrons, which just basically escape. And you want to get these alpha particles to ignite the target nearby. And they've succeeded in doing this. Now, in all the earlier experiments, the target just exploded. Once it imploded the maximum, it exploded and it cooled. And here in this first experiment they showed, and when I wrote the book, this material hadn't even been published in a scientific paper, but it was shown in 2 view graphs in 2 seminars that the Livermore people gave. And it's really an amazing result. In the August 2021 seminar, they produced 1.7 megajoules of laser energy, producing fusion energy of 1.3 megajoules. So their Q got almost to 1. And this was an online seminar in September of 2021. Let me just go back. And what you can see, what you can see is the black line here is the radius of the target. This is not cooperating. It's the radius of the target. And the red line is the temperature of the target. And this is a very difficult measurement to do, but they managed to do it. And you can see that while it's expanding, it's heating. And there's no other explanation for that other than the fact that they produced a burn wave, which is what they were trying to do. And they produced something like this at least 15 years before ITER had a much larger system and wants to produce this. Then in the October 2022 physics meeting, which I observed online, a guy named Lawrence Divol showed a similar plot. He showed it in a different way with a color profile. And red means it's burning and blue means it's expanding. And first you get a color like this, where it's just igniting in the center. And then you can see the heated area expanding while the whole plasma is expanding until finally the expansion takes over. One thing about the Livermore experiment is that a lot of the energy is wasted. Here's a graph from Livermore of they produce the laser energy into the hull room, which produces X-rays, and only about 10% of those X-rays go to the target. And a alternative scheme, which NRL has tried to do, and Rochester too to a certain extent, is to just illuminate the target directly with the laser. And these experiments haven't been done yet, at least not on the scale that these have been done. And I think John Lindell expressed it best when he thought of this. This is a very preliminary result that he got. And he said, well, experiments doing it with direct drive like this, or indirect drive like liver has been doing it, or doing fusion, direct fusion, just directly using the fusion, or fusion breeding, trying to use fusion to produce fuel for nuclear reactors. These are very difficult, complicated issues, which our descendants will have to sort out. And I thought he put it just about right. So that's fusion. And let me hopefully talk fairly quickly about fusion breeding. One thing about fusion neutrons as opposed to fission neutrons is fission neutrons are at an energy of about 2 mega electron volts. Fusion neutrons are about 14 mega electron volts. And once you have energetic neutrons, you can produce more neutrons. And here are the cross sections for producing neutrons in a lead target. And above at 14 megavolts, the fastest thing the neutron does is produce another neutron. And lead is hardly the ideal target. You can engineer these targets in a lot of ways and get beryllium. A beryllium target would probably produce 3 or 4 neutrons from a single fusion neutron. So these neutrons that you produce can not only produce the tritium that you need for the fusion experiment, but are there for other purposes too. And it can produce it can produce fissionable material like U-235 or U-233 from what's called fertile material, which might be thorium or U-238. Here is a schematic of the fusion breeding reaction, which was also on the cover of the book. And you have deuterium and tritium coming together, forming their fusion. And out go an energetic alpha particle, but not that energetic. Out comes a fusion neutron. And that fusion neutron goes into thorium and absorbed by thorium. And that new nucleus of thorium is unstable. It spits out an electron and produces an element called protactinium, which is one element up the periodic chart from thorium. Protactinium itself is unstable, and it spits out an electron and produces uranium-233, which is an element that doesn't exist on Earth, but is a perfectly good nuclear fuel. And you can mix this U-233 with uranium-238, just like you do with U-235, and it's a perfectly good nuclear fuel. Now, you can ask yourself first, well, if you can do fusion, why not do pure fusion? Why do fusion breeding? And the answer to that is that fusion breeding makes many, many fewer demands on the fusion reaction than pure fusion does. The example I just gave for ITER was that it would produce 10 times more energy than the energy that goes into it, which isn't nearly enough for pure fusion, but it's just fine for fusion breeding. If ITER works the way we expect it to, or the way we hope it does, it's fine for fusion breeding. And you asked, why use fusion breeding instead of fission breeding? And that's also very simple to answer. In a fission reaction, you have maybe one extra neutron, maybe a half an extra neutron after you continue the chain reaction and exceed all of the waste products. I mean, a lot of ways neutrons can get absorbed, which don't do you any good. And you've got maybe half a neutron left to produce another U-230 plutonium atom or fuel atom. So if each fusion reaction produces half a extra neutron, that means it takes that means it takes two fission breeders to fuel a single thermal nuclear reactor. On the other hand, fusion reactant produces about the same number of neutrons, but the fusion reactor isn't even 20 megavolts rather than the 200 megavolts. The fusion reaction is much less energy than the fission reaction, but it produces the same neutron. So if the fusion reaction produces 1/10 of the energy of the fission reaction, and then you use that and you use the fusion reaction to produce a U-233, then it's a one fusion reaction can fuel 5 or 10 thermonuclear reactions. So if you can pull off fusion breeding, it's a much more prolific way of fueling thermal reactors than fission breeding, and you may be able to pull off fusion breeding way before you can pull off pure fusion. So that is this logic for it, and that also gives what I call a possible energy structure which is sustainable. What you've got here in the letters A is the low security fence, and this is what I call the energy park, which I call more than a dream, but much less than a careful plan. You have the energy park, which is 5 thermal reactors in it, light water reactors maybe. And then you have C, which is electricity going out, or you might have a liquid or gaseous fuel manufacturing plant from the energy, and you have a pipeline for that. And then here is where you store your, here is where you store, and the waste from these 5 energies is about 1,000 pounds of plutonium, 1,000 kilograms of plutonium, which we know how to separate. So what you want to do is inside a high security fence, inside, you want to have the material which has proliferation potential, which is plutonium waste from these reactors, and you want to burn the plutonium in a once-through process just burning it in a fast neutron reactor, which burns any actinide the same way. Inside the fence also is a fusion reactor, a fusion breeder, which breeds U-233. Inside here, it's diluted with U-238 to give the conventional mixture, which is not a proliferation risk. And here is where you separate this. The reactant fuels go right into the high security area where you're separating out the plutonium. And there's nothing in here. There's no material with proliferation risk, which is not burned right away or diluted right away. And then the fusion fragments, the strontium, the cobalt 60 or whatever, just goes to cooling pools or encased somehow, and but there's no plutonium in them, and they last for something like 500 or 600 years, which is a time human society can reasonably plan for. Not like the 500,000 years it would take for the plutonium to become inert. So this seemed to me like a possible a sustainable nuclear architecture, which could supply the world at like 20 or 30 terawatts, about as far into the future as the dawn of civilization was in the past. And it's environmentally sound, it would be economically sound, and it would provide this power with little or no proliferation risk. And I guess what I wanted to do is read a summary of this. Let's see if I have it. Yeah. So that's really the guts of what I have to say. And the part on fusion and fusion breeding were very much abbreviated. I will read the little summary I have of it all. In the first part, the problem the world confronting us is inequality of power. Most of the world lives on 20% of the power of the more developed countries. And to write this, most of the developed world is turning to coal. And pious lectures by Al Gore, John Kerry, Leonardo DiCaprio, and Bill McKibben as they travel the world in their private jets is not going to stop this. A turn to nuclear power as rapidly as possible, supplemented ultimately by breeding, I think is the best long-term hope. Two, the climate hysteria is an example of mass delusion, just as Dick Lindzen says. The climate has always changed and always will, but there's no climate crisis. You don't have to be Sherlock Holmes to figure this out. Dr. Watson is perfectly capable of doing so. The information is very easy to find in a simple Google search. And it's really amazing that the mainstream media not only has not done this due diligence, nor has it discovered the tens of thousands of extremely qualified scientists that are skeptical of claims of a climate crisis, and they're so skeptical that they sign petitions disputing it. And three, to combat this non-existent climate crisis, we are told we have to spend many hundreds of trillions in the next 25 years to disassemble our power system, which basically works, replace it with another which barely works and only works when the sun shines or wind blows. In other words, half a power system. This reminds one of another tragedy in 1940 when France, confronted with a hostile, powerful neighbor, invested what today would be tens of trillions of dollars, as well as enormous effort in a gigantic white elephant in steel and concrete, half a wall. As a result of this mistake, the French were basically enslaved for 4 years. Fortunately, there were others to rescue them. But who's there to rescue us? The comparison is apt. 4, fusion and especially fusion breeding are real possibilities, but are very, very difficult to pull off. Its history is one of remarkable accomplishments, but almost always after years of delays and cost overruns. It, and especially fusion breeding, is one of very few possibilities for sustainable power at 40 terawatts. It should be supported, but not held to arbitrary cost and achievement schedules determined by at the outset by bureaucracies. There are almost always going to be surprises, and these surprises are not going to be good surprises. Furthermore, laser fusion should be supported at least on the same level as magnetic fusion, and not only for nuclear bomb simulations, but for energy. If it takes a decade or two more to pull it off and a few more tens of billions than current estimates, it's no big deal. There's plenty of fossil fuel and nuclear fuel for a few more decades. If we can waste hundreds of trillions on windmills and solar panels, we can certainly afford a few tens of billions for more fusion efforts. And 5, fusion breeding has always been the ugly duckling of both the fission and fusion worlds. Often it's been disparaged by such ignorant comments as it confines the worst aspects of fission and fusion. But fusion breeding has real potential. Let's turn it into the beautiful swan, which is what it is. Thank you, Tom. I hope this was a decent...
Yeah, it was more than decent. That fantastic stuff. I just wanted to reiterate that your book is called Mass Delusions, How They Harm Sustainable Energy, Climate, Policy, Fusion, and Fusion Breeding. Came out May 31st of this year, 2023. I have it on Kindle and it's out in paperback, right?
Yes, and the Amazon ad for it has those five editorial reviews of it, which I was very proud and very fortunate to get.
Excellent. And then also you're writing for some stuff for What's Up With That, right? You just had something out there this week, I think.
Yeah, right. That was just a comment on the Republican debate, and I thought it was technical, but I looked at all of the comments, and the comments were Trump is wonderful, Trump is terrible, Biden's wonderful, Biden's terrible. All the comments were on the politics, which wasn't my intention at all. I was talking only about the technology and the science. Yes, what really surprised me is that when Vivek Ramaswamy said that the fusion, not the climate, I forget his exact words, something like the climate panic is a hoax. And he got booed by a conservative Republican audience. If anyone would have been sympathetic to that, it would have been them. And that just shows how much of a mass delusion it is, in my opinion. And the other thing I mentioned in this was something that Nikki Haley said. They said, well, what are you going to do with China who wants to build coal power plants? And she said, well, I'm going to shake my finger at them and tell them that they can't do that. Well, in the what's up with that, I said, these countries aren't going to be intimidated by you shaking your finger at them. They want what we've got. And that was the what's up with that, the thing that I submitted.
Thank you for doing all this work. This is brilliant stuff, and I'm very honored to have you on here. Thank you.
Well, thank you. I'm honored to be a guest. I know it puts me in the same on the same list with some of the people I call my heroes.
All right.
So that certainly is an honor. It's certainly an honor to be on with Will Happer and Patrick Moore and Doug Lightfoot and the likes.
All right. I will talk to you next time then. Thank you. I hope to have you back on again.
Okay. Thanks then, Tom.
Bye.
Bye.